Hi, I'm Céline Pirou. I'll be the chair this morning. I have enjoyed a lot the first day of this meeting. I'm very much a UVES fan myself, having been involved from commissioning with, looking at one of these high redshift quasar, observing in parallel, and of course, looking at how we can implement the pipeline products into the ESO archive. I'm very pleased to introduce a set of three great talks this morning, starting with Michael Murphy from the Swinburne University of Technology. Hi, Michael. Thanks for keeping up late.
That's all right.
So Michael has also been a great contributor to exploiting UVES data with the goal of looking for the variation of fundamental constants, and that, I guess, meant looking very closely at the wavelength calibration of that instrument, including, laser combed frequency comps, and also, in fact, more recently contributing into making some of this huge data set built over the years available to the wide community. So I'm really looking forward to your talk, Michael. Please, the floor is yours.
Thank you. I hope you can all hear me clearly. Just tell me if not. Thank you for this opportunity to tell you about the work that UVES has contributed to in testing with quasar absorption lines, whether the fundamental constants of nature vary over those very large time and distance scales we have access to in astronomy. So I'll first talk to you about why, why the question of varying constants, those two contradictory terms, is meaningful and actually very important, and how we do this with quasar absorption lines. How do we actually measure the constants with quasar absorption lines? So I'll then talk about, of course, UVES's 20-year sort of contribution to this area, and it goes hand in hand with the Keck high-res contribution as well. They're both very similar in the spectra they produce, and so can both be used and have been used in this field. And then this story of the distorted wavelength scales that Celine referred to. And then I'll also talk about, of course, what the future holds and try to give some recommendations here about what an upgraded UVES blue arm should entail. So I can't really talk about this topic much at the moment without reflecting on the contribution of not an instrument but a person, that is John Barrow, who passed away last month, not very old, and he was a wonderful colleague and inspirational mentor as well, someone whose books I read from even before I got into this field in about 1999 as a student. I'd read his books, and he even wrote one as we were working with him in the early days around 2000. So if you haven't read some of his books, I do recommend them. They're really enjoyable reading, very challenging, that first one on the left as well. So give it a go. But he was a wonderful person, and it's sad to see him go. So the two constants that I'll be talking about today are the fine structure constant, the strength of electromagnetism, that's alpha on the left, and the proton to electron mass ratio on the right. That's what I'll call mu throughout the talk. These two constants are the ones we focus on because they're the ones that manifest themselves in spectra. So obviously the electromagnetic strength sets the scale of energy, or the energy scale of transitions in atoms and ions, whereas proton to electron mass ratio sets the energy scale for vibrations and rotations in molecules. And so we can look at the spectra of ions and atoms and molecules to constrain the values of these numbers. But why bother? What is a fundamental constant, and why do we think it's fundamental, and why do we think they're constant? It's really an important thing to explain. It's important to realize that we only think these things, we only call them fundamental because we have absolutely no idea what they mean. They appear in our theories. The standard model of particle physics and gravitation as well have these numbers in them, but we don't know what they are. We can't use the theory itself to explain what they are, where they come from, whether they're constant, what values they take, or anything. So we have to go into the lab here to understand whether they are constant at all. And of course, we wouldn't call them fundamental constants unless we found them to be constant in the lab, but we have to actually measure their values because the theory doesn't tell us anything. And some of these experiments, I don't know if you can see my cursor, but these are laboratory experiments using atomic clocks in particular, are some of the most exquisite experiments on the planet. And they really limit the variation in alpha, for example, down to 1 part in 10 to the 17 per year. These are sort of experiments that run for 2 or 3 years, but are bound to the Earth. So it's a very, very small part of space-time that we're probing there. And it would be much better if we could understand and answer this question of whether the constants vary on much larger scales, both time and space. So Feynman, of course, sort of restated all of the above much more eloquently. I'm not going to read out the quote there, but it's basically a summary that says you really need to think about these constants because they are a hint to us that there's some standard model, and indeed probably that the standard model is incomplete and that there is a more fundamental theory somewhere that we ought to be trying to find. So probing, asking whether the constants vary is really about testing for beyond standard model physics. And so that's why it's an exciting field for me. The main motivation is really what I've summarized there. So how do we do this with quasar absorption lines? They seem like a long way from being precise atomic clocks that you can control so well in laboratories. Well, if we take a spectrum of a quasar looking back through the vast reaches of the universe, our lines of sight often pass via the outskirts of galaxies, and those galaxies imprint an absorption signature into the spectrum. Here you've got the Lyman alpha hydrogen signature, and redwoods of that Lyman alpha hydrogen signature falls within this Lyman alpha forest. All these other absorption lines are due to the hydrogen signatures of intergalactic medium clouds, whereas this nice big deep one is from this galaxy. And these nice sharp, well separated features that you see in the red part of the spectrum, redwoods of Lyman alpha emission, are the metals in that galaxy. And those, the relative separations between those lines is like a barcode encoding the value of alpha in these distant galaxies. So if you can measure a deviation in that pattern that you expect from laboratory experiments, then that can tell you that alpha has varied relative to what you have here on Earth. So that's where we look for alpha. We use the metal lines, redwoods of the Lyman alpha emission line. And way down here in the much bluer part of the spectrum, we see molecular hydrogen lines as well in a few of these DLAs. Now, Pasquier Notre Dame's going to give a talk after me about all the wondrous things that he's been able to do with molecular hydrogen absorption over the years. So I will focus mainly on alpha in this talk, but I'll make reference to the results that come from molecular hydrogen studies. But you can see that they're way down here in the blue, and they're in this Lyman alpha forest region. So although the principle is the same, you're looking for relative changes in the wavelengths of those lines relative to each other, the analysis is much harder because you're in the Lyman alpha forest where there's lots of confusion. So what happens when you change alpha to all these lines? Well, I've mentioned already that this barcode that you see in black at the top, where delta alpha and alpha, the relative change in alpha is 0. That changes as you decrease alpha in this case. So you can see that these lines shift by large amounts in the case of iron or zinc or chromium, heavy atoms, whereas light atoms don't shift by much. Their transitions don't shift by much at all, aluminium, silicon, magnesium. And so what you end up seeing is a characteristic pattern of relative line shifts where the velocity, what you're looking for is a velocity shift of one line relative to another. And you can do this with many lines at once. And so the scale of this is such that you have a 20 meter per second variation between lines for a 1 part per million variation in alpha. So you can see that if you can get down to 20 meters per second velocities, you can really put some pretty impressive constraints. A 1 part per million constraint, it's hard to think of other areas of astronomy where that's kind of the standard. So it's a pretty impressive way of measuring fundamental constants. What does it really look like? I've drawn absorption lines so far as just stick figures. That's not very good, because one of the great innovation, one of the wonderful things we were able to see with UVES and Keck high-res as well, was actually the full velocity structure. Resolving the velocity structure of these absorption lines was a really important part of the process. So you can see here I've got 3 different transitions from one absorption system here at this higher redshift 2.2, and you can see that it's not just a single sort of Gaussian-like absorption line. It's made up of a whole bunch of absorption lines. There's a whole velocity structure that is pretty much copied from one ion to another. And it's our job to then fit this absorption structure. We don't know what it is a priori, and we have to use the data to tell us what the best fit is. And that is what I've marked in green over the top of the black spectrum. So if you vary alpha by 1 part in 10,000, you get this change in the spectrum. You can see that the green line is shifted from the data in iron by a noticeable amount, whereas the shift in magnesium and aluminium, these lighter atoms, is not nearly as much. So that's the actual signature that we're looking for in the data, and that's the quality of the data we'd like to see, and indeed what we get from UVES and Keck high-res. So when I started this work with John Webb as my PhD supervisor in about 1999, there were really kind of, I think, 3 revolutions going on, which really made this an exciting thing to do. Firstly, of course, we had that many multiplet method, this way of looking simultaneously at all the different transitions and their sensitivity to alpha on the left. And then we'd had some years, about 6 or 7 years, of build-up of Keck high-res data. So a lucky few people had been observing quasars for that long and had built up data that they then gave to us, luckily. We were very fortunate to receive the data in reduced form, and we didn't really have much more than that. But that allowed us to get a 10-fold precision gain on measuring alpha in these absorption clouds. Prior to that, people had only really used doublets, and they're not very sensitive to alpha, etc. And they had not very good data, of course, not like we have from Keck high-res and these days from UVES. So, of course, when you increase the precision by a factor of 10, a whole bunch of systematic errors that you didn't think about before become very important. And that was, of course, what we then struggled with for the remaining sort of 10 years of the work I'll be telling you about. UVES, of course, started observing around 1999, and that's when the Quasar archive was started building up, and that was fundamental to the progress in this field, as I'll show now. So, by about 2004, we built up this sample of 143 absorption systems where we'd been able to measure alpha. And what I'm plotting here on this plot is versus redshift. We've got the value of delta alpha and alpha, the relative change in alpha in units of 10 to the minus 5, for all of those 143 measurements with their 1 sigma error bars. And so the bottom panel sort of zooms in a little bit on the vertical axis, but also bins up the data from the top panel so that you can sort of see the overall trend. And basically summarize the results there. There was this strange deviation from 0. You seem to think that the value of the fine structure constant was smaller at high redshift. Obviously, very controversial, very strange result that you really want to look at the systematic errors for. And of course, that's what we spent a long time doing, and many others in the field, trying to understand what was wrong with these results. We couldn't really find anything compelling. And so, of course, the thing you really want to do is have another spectrograph of similar quality or better if possible. And of course, that's what UVES gave us. Over a long period of time, we were able to reduce a large amount of spectra, large number of spectra, and make a similar plot, but with UVES this time. And we don't see the same result. It would have been wonderful to see the same result, but we don't see the same result. At lower redshifts, we don't seem to see any result at all. It's pretty much consistent with 0. And at high redshifts, it's sort of maybe slightly above 0, but certainly not the consistent below 0 result that we saw for Keck. So you might think that the story stops there, and indeed, your natural explanation for this is that there's just something wrong with both of these spectrographs, that maybe the calibration, the wavelength calibration is wrong. After all, that's the principal calibration involved here. Strangely, though, if you plot these results up across the sky, and remembering that Keck and VLT see different skies, you find that there's actually evidence for, sort of 4 sigma evidence for, an internally consistent evidence, strangely, for basically a gradient of alpha through the universe, that if you sit at one point and you see a dipole variation across the sky. Very, very odd, but really the only other way of sensibly plotting the data, basically. This dipole in red that you see is the direction of the dipole if you use all the data together. But if you split it up by a telescope, you see that, strangely, the 2 telescopes agree on what the dipole is. So if they're wrong, it's pretty weird result. Furthermore, if you combine the data together and then split it up according to redshift, you see the same thing. So it's a bit, that's very strange if systematics are responsible for what we were seeing. So of course the big question is, well, really, is this really true? Most people, of course, don't think it is, and many other people tried to study a smaller statistical sample coming from the first large program for quasars from UVES, other individual absorbers from UVES by Levshikov and Malaro in particular, where they look in detail at very high signal-to-noise data to try and understand the process of measurement much better. All of these results ended up being basically consistent with that dipole. So you couldn't remove the evidence for the dipole, even if you think it's very strange, which I certainly agree with. The main thing, of course, is, well, what are the systematic errors that are explaining this? And these days, I think, recognize that the work that Paolo Malaro did in 2008 was a real step forward in this direction, trying to understand the systematics. He used asteroid spectra, so just reflected sunlight, to get a second calibration. So the thorium-argon calibration you get at the telescope that we do with the quasar work, and a laboratory reference solar spectrum that you can compare your asteroid spectrum to try and get another calibration of the spectrum. So you get a thorium-argon and a solar calibration as well, a solar laboratory calibration. And what he found was that the UVES's calibration was fine, strangely. So everyone thought, oh, that's odd because there seems to be problems with the data. So that wasn't the explanation. We did...
Michael,
yes?
5 minutes.
Sure.
5 minutes.
Yes, I understand. So the next step was to try and expand that technique and make it more precise and try to see whether it was applied to all quasar spectra, both in high res and UVES. And we expanded this by also looking at other solar spectrum, basically solar twins. They have a solar spectrum in them, more or less. And so that technique worked as well. But what we found was very different and basically ubiquitous across any spectrum we looked at, where you see this long-range distortion in the wavelength scale of VLT UVES and Keck high res. So what I'm plotting here is on the vertical axis, the velocity difference between that thorium-argon wavelength scale and the solar wavelength scale. And you see that it varies strongly and is sort of almost, sort of 500 meters per second in amplitude in the blue arm of UVES and in the red arm. The problem is, of course, this isn't constant. It changes from, over sort of several day timescales, seemingly, maybe different telescope setups or spectrograph setups. Generally speaking, the opposite distortion was seen in Keck, but you can start to see that this is a pretty worrying distortion, because it means that transitions measured in one wavelength over here and over here will have a velocity shift between them when you register them on a velocity scale. So this is really undermines any confidence you have in those previous results. And it's a really big problem that still isn't really solved. We don't know where these distortions really come from. However, we can use this asteroid or solar twin technique to get a better calibration for new observations that we've undertaken. So all of the previous results were taken from archival spectra, by the way. These observations here on this plot were from new data taken in a dedicated way that we could correct for these problems. And so there's 27 measurements, and I've binned all the measurements for an individual quasar up onto one point so that I can plot it versus this x-axis, which is the angle away from the dipole on the sky. So you would expect to see, if the dipole was true, this grey band that you see on this plot. But actually, the data don't seem to agree with that at all. There's no evidence for varying alpha at the 1 part per million level, and certainly no real strong evidence for the dipole. So What about mu? Well, as I mentioned, Pasquier and his colleagues have discovered almost all of the molecular hydrogen absorbers that we know. They've all come from UVES, and here I'm just plotting a comparison of the UVES data and high-res data on one of the absorption systems, where you can see some of these molecular hydrogen lines here with a double peaked at velocity structure. And so Pasquier will show you many more of these. The results are similar, but many, many fewer. It's hard to find these molecular absorbers, as Pasquier will tell you. And these measurements at higher redshifts are all from UVES, basically. The red points have not been corrected for the distortions, whereas the white points have been. And you can see that the sort of precision you're getting down to per point is about 5 parts per million. And then the only basically, you need to have very blue spectra to do this with UVES, and that's why many of these results have come from UVES. You have some competition at low redshift where there's a few absorption systems known where you can get radio millimeter molecular spectra of different molecules that are more sensitive to mu variations. So they give tighter constraints. Nevertheless, at higher redshifts, UVES is the only game in town at the moment. So is ESPRESSO knock this out of the park? Obviously, it's a super HARPS. It has excellent wavelength calibration. So its wavelength coverage, though, is the key thing. And for this wavelength coverage in ESPRESSO, alpha is okay. You can measure, for most redshifts, the important lines for measuring alpha. But for mu, you really can't measure much. And I'm sure Pasquier will show you in detail why. The organisers wanted me to say what I would upgrade in the blue arm. Of course, I think that ESPRESSO is really for alpha now, whereas UVES is for mu. And I think there is a precision gain and accuracy gain available. We really do need reliable constraints on mu. We don't have many reliable measurements of mu at the moment. And so wavelength calibration is really the key thing to incorporate and improve if you're going to design a new blue arm. I've made some recommendations here about how to do that. There's many different ways. I'm happy to discuss those. But I'd just like to call to your attention the fact that the red and blue arm of UVES are often misaligned. And so you can see that visually here on this plot where you see the red slit on the right and the blue slit on the left. The quasar is aligned with the slit on the left, but not on the red. And that basically corresponds to a 200 meter per second shift between transitions in the red arm and the blue arm. So you have to kind of solve that if you're going to get very good calibration. So I'll conclude with just saying that UVES and high-res, the indications for varying alpha early on were not reliable. That was because of these distortions in the wavelength. We've got basically 1 and 2 part per million precision level now from reliable and distortion corrected spectra. ESPRESSO really wins for alpha, but there is still plenty of room for improvement for mu, and for that you really need the blue coverage but reliable calibration, which includes making sure the calibration is the same and crosses over into the red. And just as Salim mentioned, I'll just finish with an ad for that large data set that we published last year, if you'd like to take a look. Thanks.
Thank you very much. So while people think about question, I wanted to ask Michael what you thought about this recent idea that was put up by Ryan Cook of doing differential measurements by using 2 observers at different redshifts that happen to have lines that are close in lambda observed, right? To minimize the effects that you've been talking about, that, the variation with wavelength.
Yeah, look, I mean, any differential sort of technique that you can use for that is useful. It limits it to very few absorbers. The problem with these distortions is that they're, I'll say, time variable. They're not the same all the time. I'm not sure if time is the variable that's important here, but something makes them change in all the slit spectrographs, including Keck VLT and Subaru's HDS spectrograph. So there's something to be solved there, and I don't think you're going to get very far with those sorts of avoidance techniques. I think it's better to try and actually get in there and figure out what's causing them and mitigate that or solve it. Of course, with ESPRESSO, you don't need to do that for alpha, but for mu, it's very important. And I don't think the differential technique would work very well with with mu.
Sure. Yeah. All right. So I think Stefano Cristiani was first.
Yeah, Michael, I have a question about mu. What is the minimum spectral resolution that would you think necessary to carry out mu measurements?
Well, for mu measurements, look, I think the resolutions that you're getting, in fact, the plot that I showed there compared two different resolutions. So the resolution of that UVES spectrum here in black is about 70,000, and the one in high res was taken under very good seeing conditions, and it was about 110,000. So there's not much difference there, although you can see that the high res lines are a bit deeper in parts. So you're doing pretty well with a resolving power of 70,000. I don't think you're missing out important information. The molecular lines are very narrow, and so if there is velocity structure, hiding in a resolution element that you need to find, then better resolution is better. But I don't think that you need to go anywhere. I don't think you need above 100,000.
No, but how low can you go?
How low? Well, I'd say that you're really pushing it if you go below 50,000 or 40,000.
Thank you.
Paolo Molaro next.
Hello, can you hear me?
Yes.
Okay. Hi, Michael. Very nice. I enjoyed much your talk. One communication, I think that there has been a new measurement in the lab that appears a few weeks ago, which improved the lab by a factor of 20. So now the laboratory limit is at the level of 10 to minus 18, not 17, okay, which for the people that is not aware of that, is like to measure the age of the universe with a 1 second precision. Regarding the wavelength calibration for UVES, I think that we have to really think what does it mean, because UVES is a slit spectrograph anyway, so you can put also a laser frequency comb, but actually this certainly helps for distortions and so on, but you don't know where, especially if you have to combine different exposures, of course, then it could be a complicated story. So I think it requires some thinking.
Yeah. The astrocomb is a possibility. Of course, it is difficult at these resolving powers, 50,000, 60,000, because you need very widely spaced comb teeth, and that's a difficult thing to do at the moment in the optical. And so that's why I've written here that a thorium-argon Fabry-Perot combination would be probably okay and worth looking at. You don't need it for the precision, but you need to know its reliability, and that's why I've got all these other measures here that could be incorporated instead of a different calibrator. But certainly it would help, and it would help diagnose any problems for sure, to have a different, more densely populated calibration spectrum.
Okay, thank you.
Thank you very much, Michael.